All right, yes, I want to see if we can talk about the very edge, the bleeding edge of analytics, some of the things that may land in tooling like Cloudera and other open source projects. But first, something much more serious. A few weeks ago, I took a delivery of one of these. First problem was no one knows what color that is. So is that yellow or green? I don't know. I have a little bit of red-green color blindness, so I'm a little worried now that it only looks beautiful to me. Two, you could see it was shipped from Munich to Portland, Oregon, and then I was shipped from Portland, Oregon to Heidelberg. And the problem is I got a text message last night, and my wife and her friends are driving this thing around. So I'm a little bit worried about the low curbs and all that. All right, more seriously. So today, I want to start with what we have today, Hadoop Analytics. So you've had enough introduction, I think, to Hadoop MapReduce, simple idea of doing an embarrassingly parallel map step and then reducing that and combining results at other machines and shuffling information through the network. And that's great for advanced analytics because there are some excellent machine learning libraries like Mahout and other projects that allow you to grab other people's code and do great things with Hadoop, machine learning, and data mining. Also, Twitter has come up with a really interesting library, Scalding, that allows you to generalize data workflows and specify the way results are combined across machines in a much more flexible manner. That's quite interesting. And then we've just talked about Yarn, the resource manager that's used under the Cloudera distro and is part of the Apache Hadoop stack. And that allows us to schedule application containers for other things like Apache Spark that I'll talk a bit about in this talk that has its own libraries for machine learning and data mining and that is really fast for iterative computation. And so that's, it's sort of the broad landscape of where we're at today. Now, what I want to talk about is some of the trends. So we've talked about ad nauseum about the 3 or 4 V's of big data. I want to focus on some very specific trends and how they're playing out, what the problems are, and what I see in terms of some of the early solutions in terms of the expansion of data primitives that are being used beyond tables and collections and vectors and key values. Then talking a bit about speed. We just talked about streaming a bit. I'll go a little bit more into the streaming and the streaming debates. Complexity. As we see pipelines put into commercial production, it's becoming more than running a single machine learning algorithm in a vacuum. We're talking about how did we get data into the algorithm and how do we score information coming out of the algorithm, that whole pipeline. The intelligence that is needed to make machine learning easier to use and easier to use in data exploration and data operationalization. I will talk a bit about how we can turn machine learning on itself to solve that problem. And then finally, there's a drastic gap, as we know, between someone asked a good question about it earlier, like who is to use these systems? What kind of skills do they have? There's a massive gap between the technologies that we're using in big data analytics and the people that are coming out, the workforce that's supposed to use these things. So do we educate them? Do we build easier to use tools? What do we do about that? So this technology is really interesting in terms of a number of real-world applications. These are some of the ones that we're looking at with our customers at Intel, working with Cloudera and working with other open source projects to get solutions in place. Lots going on in life sciences, particularly around cancer research and personalized medicine. Education's an interesting area too, where graphs and other advanced models have been applied to recommend different approaches to educational material. Network security, I'll talk a bit more about that. And of course, retail. Retail's a massive market, and it's got some what seem like mundane problems, but they're quite fascinating from a technology perspective as we bring new things to old problems. All right, so variety. What do I mean by data variety? Variety is the idea of using different data primitives to do the right job, applying them for the right job. At the bottom, you see different data models. We've got keys and values, document stores, columnar databases, and NoSQL stores. We have graphical models, arbitrary relationships between objects that represent something in the world, and SQL tables. These are all important models, and we want to build systems going forward that can build and consume these types of data models that we can apply different access models to, as you can see, and that we can implement and expose to application developers in different ways. Today, some of these things are integrated into these systems, but not all. It's very difficult to flexibly work across the boundaries of these data primitives. In some of the data processing pipelines I'll discuss, we actually want to use many more than one of these data primitives to solve the same problem. So it's important that we figure out how to handle these. One that's particularly difficult to seamlessly integrate with the others are graphical models. So these are really interesting to me because they're also very powerful models of the world. They apply in many cases when you have a natural information network, like the connections of the human brain or the web links in the web, the internet graph. Or when graphs are also very useful when they naturally express an algorithm like a neural network or a Bayesian inference network. I mean, many algorithms are just cast in graphical form, and it's actually more difficult to cast them in terms of factorized functions and so on, and very computationally inefficient. Of course, when you're looking for particular relationships in social networks and elsewhere, there is also search for graph search. Facebook talked about that, what, a year and a half ago? We did a demonstration of graph search as well, where you find these golden path connections within Wikipedia and other data sources. How can you explain the closest connection? And of course, graphs can be used as an abstraction for algorithms, and we can show an equivalency between sparse matrix computation and graph. All right, so we're eating some of our own dog food, as we would say. We're actually applying graphs in real-world problems with customers. Here's a graph we built that's tens of millions of nodes with a broadband service provider in Canada. The nodes represent channels. The edges represent channel switches. So this is a surfing pattern graph. How are people viewing the network at any given time? Can we make recommendations about channels that you might be interested in from such a graph? By running graph algorithms and looking for the most tread paths through the graph, we can make interesting recommendations that are very personalized. You might have heard that Intel sold off a business to Verizon recently. It was an Intel Media set-top box. We also had a recommendation system behind that we did not sell off. That recommendation system recommended movie content to users based on a graphical model. By going back to that golden path in graph search, finding the least cost path through a graph, we can make a multi-dimensional based recommendation based on the user preferences of an individual user and the content we want to recommend. And these graphs can get very large. Another one we've done with McAfee that's now a fully integrated part of the company, Intel Security. In this case, we took ground truth data and the connections between domains and URLs and other types of objects in the internet. We were trying to infer maliciousness of unknown gray areas of the internet. And so we built the graphical model. This one shows a couple 100 million edges. Actually, we built one that was 7.5 billion nodes and 15 billion edges. And we run that on a medium-sized compute cluster. And then we propagate messages among these connections that are the estimations of neighbors' beliefs about the maliciousness of their peers. And by doing so, we can take a graph like this is the actual graph that we used for this belief propagation on the semantic web. And you can see that we have reputations. These are the priors. This is what McAfee knows or Intel Security knows by running those client applications that look for infections from viruses. So we have a really good set of ground truth. We know that when you visit a file or visit somewhere in the web, whether you're going to get infected or not, or whether you got infected. But by applying loopy belief propagation, we were able to, you can see a subtle change here, to score many more of these reputations, more specifically outside of the gray zone, accurately. So to make inroads to handling these interesting variety of data primitives, Spark is a great thing for that. It's gone way beyond what else is out there in the open source. You can see here an example of Spark Stack. It's got a common in-memory data structure that you can cast into different types of specific data models. And that's useful. That means that you can use the same underlying resiliency technology on the Spark engine and solve different types of data primitive problems. So you can see that we can get to it through Spark SQL. We can do streaming on these data structures. We can do machine learning and data mining on them. And we can even do graph processing with the GraphX library. And so we're working with that. I'll talk a bit more about that. Another interesting thing is the grades workshop is a co-located ACM workshop, and an interesting paper came through it last year from SAP. SAP's been working on graph as well. So another way of dealing with variety is to unify at the database level, in-memory database level. And you can see that on the left-hand side is a standalone relational database. And on the right-hand side is one that's got some graph logic integrated into it. So graphs are very hard to process with relational databases. To traverse hops in a graph requires many join operations. And it wreaks havoc on indexing as well because you have to do a bunch of step-by-step indexing searches over and over and over for every hop. So what's interesting is that they did some work to optimize the existing relational structures to handle graph data objects. And here's an example of the execution of a query. So you do a select operation where you're choosing the vertices and edges that meet your criteria. You do a traversal to hop from one to the other. And you do a projection where you return just the results you're interested in from the resulting search. And you can see that in a traditional database, you'd scan from the source to the target vertices. You'd be scanning to look up the target every time you hit another source. And you're hopping back and forth in this table. So we know that if you're transitioning edges of a type, it's hard to read, I'm sorry. There are some edges here that are of type A. You're going from here, and you're looking for all connections that are of type A. To B, to A, and C requires you scanning back and forth in this to do that traversal. So they optimized their existing index structure with a two-step index that will allow them to do a very short scan and then a block lookup that allowed them to get really good performance. So there's an encoding that they presented in the paper, and then they compared the results. Again, it's sort of an eye chart, sorry. They loaded a bunch of the common open data sets for graph involving co-product recommendations at Amazon, roadmaps, and so on. And then they compared the execution time as a function of how deep you were traversing the graph. And so the good news is that the blue line is the reference for scan, and the other lines are different block sizes they used with this new approach. So this is very fascinating to me, not only because I'm chairing grades next year, and I invite papers, by the way, in graph processing, but because I think this is where it's going. I think we're going to see graph just consumed into the existing relational databases and other parts of the architectures. And that's really bad news for these standalone graph database companies. All right, so speed. Yes, so Hadoop is meeting the Internet of Things. Internet of Things, all this device data, machine-generated data, it's been there for a long time, but it's getting, as we know from wearables and other trends, much, much larger. But what's interesting to me is talking about the data center side of this connection. What kinds of user interfaces, services, analytics, and so on do we have to run to support those devices? And where do we do the analytics? How much is done at the edge? How much is done on the device itself? What do you do on the device if you're solving a machine learning problem? What do you filter through to the cluster? What do you join there? So for Internet of Things, it really puts a larger emphasis on stream processing. Wolfgang talked about stream processing a bit earlier. We take a data stream in, we take a distributed messaging system like Kafka or Flume or any of the other good projects. When we're doing machine learning on IoT data, what we're going to do is we're going to bring it into the cluster, we're We're going to extract a bunch of feature informations. Who is this? Where are they located? And so on. We're going to build that into a model. We're going to train the model using machine learning algorithms, and then we're going to ask the system for results, inferences, predictions, and so on that. Now to do that, there are some challenges. So first of all, I think it was also mentioned, data replay. So you don't want to just know what you're taking in now, but what if you find a bug, or what if you improve your application? How are you going to replay the data that you've had? What if you have to go back and look back in time for other reasons? The other thing is that how do we do this in a better way than just speeding up batch processing? I mean, is there something more elegant we can do? And then, of course, the models we build are going to evolve over time, and there's some merging we have to do between what we know and what's coming in now. And so these are all big challenges. Now, there's some work going on in this. Some of you may have heard of a Lambda architecture where we take basically a bypass for new streaming information coming in the system, all the batch information we know. When we do a query, we can federate the query across these two sources, and that gives us some real-time response as well as the benefits of history. And you can see two paths in the Lambda architecture. Processing on, for example, Storm, which would be a streaming interface, and Hadoop out of maybe HDFS. And so this is interesting because you've got to integrate, you've got to implement your transformation logic twice. You've got to federate that information. And that's an interesting problem from a systems engineering perspective. The debate's open still. There are people talking about other architectures. As a half joke, one named Kappa, another Greek letter. Maybe a better idea would be to do everything through streaming. Now this is tough. It might be easier to implement the system with batch, but stream processing is coming along as well. So we keep a stream online. When we make a change, we record. We're also dumping information into an elastic buffer, and we keep a history window. When we want to update something, we're going to go back and play that back through a new version of the stream, a new application update of the stream processing, and that becomes a new job. Once that job has caught up with the old job, we kill the old job and we switch over to the new stream. So it's a more homogeneous architecture, and it's something that might be a little bit cleaner. But you know what? This is an open debate. I just want to raise the debate here. There's no good answer yet. And I know that a lot of people are still looking at Lambda. And in fact, Spark streaming might be one answer. So I mentioned fast batch. That's really what Spark streaming is about today. We can take these different streaming inputs to Spark, and then we take the input data stream, break it up into small batches, and we schedule jobs for each one of those, and we call that streaming. Now, the way that works is Spark actually creates a data set, a discretized data set for each window in there. And it can overlap windows, but it's still about these separate batch windows. So it can be used with or without windowing, and you can run analytics on any of the resultant data sets called RDDs. The problem is mini-batch streaming means mini-batch analytics, and it really doesn't provide a solution for merging models or do anything really interesting with the pipeline. And graph comes in here too. So you can apply that type of streaming to GraphX, the new graph library. So basically you take, you ETL in user data from collections or tables, you build graphs, you join information across them, like maybe users and product ratings to make a product recommendation graph. And then you can do inferences on that to see what the products you'd recommend. And graphics is cool because it can run, as I said, with Spark's different ways interpreting data models on RDDs. It can operate on tables and operate on graphs, and that's a really nice systems architecture. The problem is that there's no way to inject new information into an existing graph. That's not defined in the model today. So one thing we're working on at Intel is how do we actually merge information into an existing model so that we don't have to regenerate an entire accumulated graph or rerun machine learning at each window on the whole graph. And so what we're doing is we're merging information directly into the data model, and we've created algorithms that are incremental versions of classic machine learning algorithms. And it's also going to require us to revisit indexing and revisit the way we partition data to be efficient as things evolve. With the graph system can be very imbalanced over time. And I won't kill you with this. We're not showing a lot of code today, but just to show you an example of kind of the hello world of algorithms for machine learning and statistical processing PageRank. On the left would be the existing PageRank using something called the delta method. On the right is how you'd update it so that you could do online PageRank. So you could basically merge new pages and information into an existing model of the way you rank pages in, for example, the internet. And so it's quite easy to do for certain algorithms that meet certain properties. And we're getting good results so far. These are extremely preliminary, and we're not actually happy with the convergence rate yet. But when you're measuring an algorithm like this, you want to see how fast you converge. Are you getting benefits from the way you're merging information? So how fast do the results settle? And how much overhead is there in getting that settling? And we see massive gains in reducing the overhead because we're not having to shuffle around as much information and processing the graph as we do this processing incrementally. And the conversion rate is somewhat faster, although we want to get that down an order of magnitude or more. Okay. Complexity. So as the trend seems to be that the pipelines are getting more complex for a couple of reasons. First of all, again, it's not monolithic algorithms running like PageRank in a vacuum. It's a whole pipeline for data scientists. They care about the whole end-to-end problem. How do you start with the files I've got on hand or the database I have that I want to pull from, and how do I create these models and use them? Also, there's some analytics like deep learning, deep learning, machine learning. We're analyzing images using different layers of machine learning that also creates complex pipeline analytics, decomposing analytics themselves into layers. For example, this is an actual data science workflow that our data scientists worked for a problem. Every step in there is some transform that you're doing on Spark. You're reading in records in a JSON format from CSV. Actually, you're extracting path values. You're deleting columns, you're filtering rows, you're dropping information, you're joining information from two sources, a source of IP domains and events. And then from all that information, you're creating the graph and running an algorithm. So this is a very typical thing for a data scientist to do. They want to then take this thing, this big operation, they finally figured out they got it right, and they want to turn that into a tool, a primitive they can use as a processing step, and put it in a toolbox and use it with other ones that they create. So this just gives you an idea of how many steps of analytic processing people may be using Hadoop or Spark for today. It's that big, and this is a very small step in a real problem. I mentioned the other one as well. So you can apply complex analytics. Complex analytics could also be interpreted as deep learning. So machine learning that's implemented as a hierarchical, a number of steps of learning. So if you're doing image processing, for example, you might look at for different feature fineness. So the background you could see is very uniform. It may not only take one step of image processing like pathway A1 up there to process that well and to encode that information. But for the lower, like this path B3 that has 3 steps, that might be taking very fine detail in there to recognize an image like this bird. And so if you implement that type of thing, there are a lot of benefits. Deep learning is great because you can take an object and recognize it over different deformations of the object, different angles, different lighting, and so on. But and also you want to be able to do this with different scales of features, like I mentioned, and structure that's shared within the image itself. So fine-grained patterns over larger-grained patterns, and so on. Now, some of the work we're doing is to benchmark these kinds of learning pipelines against other existing ones and seeing how accurate we can do object identification. This is a percentage of accurate object identification of our work in Intel against different amounts of trained images and different existing benchmarks. And so it is improving. That means that deep learning pipelines are likely to get used in computer vision and with systems that back that for product identification and so on. There's many real-world problems this is relevant in. What's interesting is that Intel's also working through its Collaborative Research Institute in Europe to build a distributed deep learning pipeline for Spark. and to make that contribution, hopefully, into the ML library for Spark. So hopefully we'll see this stuff land on Cloudera and land in the open source communities. All right, and finally, intelligence. So you can see that it's a very complex story. I mean, the analytics are just getting more sophisticated, and so it'd be nice if the machine learning could be brought to bear on itself so that it could help select the right data to process, select the right features to build, select the right algorithms to run. This is an interesting thing, and it's been looked at in a lot of non-distributed settings before. It's called ensemble learning, so wisdom of the crowd. Basically take a collection of classifiers or other types of algorithms and combine the results to get a better output. And you can do this in different ways. You can just you can combine them, and each classifier can look at a different slice of the data, different set of features, or you can actually boost the algorithms that are performing better. And what's interesting to me from an Intel perspective is that to do this with n predictors, it takes n times the computation. So you can keep it in constant time if you scale out the number of machines, and the experiments just get a better quality. So ensemble learning is maybe one way to take some of the experimentation out of the user's responsibility and put it at the machine level, have the machines do it for you. There's a lot of downsides to it still. This is the current research work. There's a lot of tunable parameters that are required to make that work. There's a lot of selection criteria that's still needed, the user has to select. But there are companies that are starting to claim that they can have fully automated system, using them to solve cognitive computing applications and so on. No selection of criteria. So stay tuned. We'll see where this goes. But I think it's going to mean a lot more machines brought to bear on these problems, and hopefully a lot more automated machine learning. All right. So I know I'm running really low on time, but I want to, the very last subject is ease of use. So yes, composing pipelines to do all this is very, very challenging. A data scientist looks at a problem like this from end to end. And from end, we mean ingestion into the data center cluster through building those features that we put into the model, that we train with algorithms, and that we extract value from. That is their end-to-end problem. And right now, a lot of tools aren't designed for loopbacks, which is what they do while they're developing the solution. It's very painful to develop the features for the model itself. Composing the pipeline is largely do-it-yourself today, but it's getting better. It's hard to manage the state in this pipeline, especially if you're working with other users and collaborating with data science teams. And there's a lack of skills at the intersection of the systems engineering that you build these systems with and the data science that you perform on it. And you know it's a big problem. We know we're going to have a shortage of data scientists by 2018. They estimate a couple 100,000. So obviously hiring people may be a problem. And so Accenture, we looked at one solution. Data scientists, one of the problems is data scientists are required to have a ton of skill set. So from advanced analytics down to systems administration today. So one idea, they had an idea, why don't we just build a team of people to create a data scientist, right? But we're hoping we can decompose it into two parts and hire just 2 people instead of 5. The data analyst and the DevOps person that administers the system. That's traditionally what you do in deployment anyway. But some of the challenges include the programming languages that are used in these systems today. Here's an example of Java running the hello world of Hadoop. Again, it's word count. It's the simplest thing you could ever program on MapReduce. It's still a large program. There's a segment of it. There's the program. With the systems we're building now that are in scripting languages the data scientists actually use, they use things like MATLAB and Python and R. With that length of a script, they could practically code an entire pipeline that we showed earlier, not just one step of word counting. So clearly, these languages aren't appropriate for data science. So one of the solutions is to decompose the problem like I mentioned. Take the analysts and let them interface with the UIs they're used to and the languages they work with. Create a nice data science API to allow those languages to relate to these back-end tools. Let the DevOps person deal with the stuff on the right. Make sure you can do machine learning on both sides of the connection that's similar, so you can develop on one end and then publish the script at scale and run it on the cluster. Same with the data wrangling, both sides of the connection. So the key is to have a good API in between that can allow you to do the ETL and feature engineering, allow you to do the analytics on it. For example, you could run a popular machine learning algorithm through a popular interface, REST. It's a hypermedia interface. You express the parameters of the algorithm, and it gets run on the system back end. The system knows how to interpret this. This is a very good protocol for it, and it can get information about the execution of that algorithm and other things that can do the system just using URLs. And so what Intel's doing is building a system that starts with the foundation of Cloudera, so it's scalable throughout the full pipeline. We add data wrangling, so we can do string manipulation, math operators, and graph construction. We're supplying new machine learning libraries that are ready for commercial deployment, not the ones that are in open source, graphical algorithms, classic algorithms. And on top of that, we're putting this data science API and publishing these libraries and getting partners to build these other tools so that the data scientist gets a data science experience out of the system. That's the Intel Analytics Toolkit. I don't have time to go through this, but there are a number of algorithms that can run on that toolkit. They're graphical and non-graphical, and it's completely seamless. And by the way, there's a lot of research going on in this space too. One of our centers at MIT is working on it as well. So we may not just unify around REST and the type of API I talked about. We could also use a common query language that federates these backends. Here are a bunch of other projects, and they could be federated through this new query language project. So this narrow waist idea of relating, the data science tooling to the back end is becoming very popular. All right, so stay tuned for updates on that particular project, and contact me if you're interested in that query language approach. So anyway, to conclude, I have a technology wish list. There's a bunch of things that, although we're solving a bunch of problems at Intel that we wish we had, take a look down this list. Let me know if you have one of these technologies. We talked about databases, but there are many things. One of the biggest problems is auto-configuring Hadoop clusters to run well. And so my call to action is this toolkit that I mentioned that does this relating of the data scientist to the DevOps problem. That's available as a beta right now. So contact me if you want to get involved in the beta program. And also, if you're in graphs, if you work on graphs, consider submitting a paper to grades. Sorry for running long. That was a lot of information. See if we have time for questions.
So Taylor, thank you very much for this strong overview and also explaining the challenges around that. So since we're going a little bit short of time, I will give you opportunity of one question. Other questions? At all? So possibly not. So I will have.
I haven't even caught up with my own talk yet. So.
So then I would simply propose for you to have the opportunity to discuss directly with Ted. Ted, thank you very much for your nice talk, and I really appreciate also the key part of education, the ability, to have people who are able to use this technology. So thank you so much.
Yeah, thank you.